42,000 years ago, the northern lights appeared over the equator. Auroras shimmered across African skies, above Australian deserts, throughout the tropics, brilliant curtains of green and red where they had no right to exist. This wasn't a spectacle, it was a symptom. Deep within the planet, the magnetic field that shields Earth from space radiation was collapsing. For roughly 1,500 years, that shield operated at less than 10% of its normal strength. The magnetosphere, our barrier against solar wind and cosmic rays, had effectively gone offline. What followed was a planetary crisis that coincided precisely with the disappearance of the Neanderthals, a pulse of megafauna extinctions, and the sudden emergence of cave art. The sky had changed because Earth's invisible architecture was failing. Earth's magnetic field originates nearly 3,000 kilometers beneath the surface, in the outer core, an ocean of molten iron heated beyond 5,000 degrees Celsius. This liquid metal churns in massive convective currents, generating electrical currents that produce the magnetic field extending tens of thousands of kilometers into space. This system, the geodynamo, creates the magnetosphere that deflects solar wind and galactic cosmic rays. Under normal conditions, the field has clear north and south magnetic poles aligned roughly with Earth's rotational axis. This organized dipole deflects the solar wind, charged particles flowing from the sun at over 400 kilometers per second, and scatters galactic cosmic rays, high-energy particles from distant supernovas moving at nearly light speed. The geodynamo is not stable. Flow patterns in the outer core shift over centuries and millennia. Sometimes the system destabilizes catastrophically. The magnetic field weakens, poles wander, and in extreme cases, they swap places, north becoming south. These are geomagnetic reversals, when permanent, and excursions, when temporary. Around 42,000 years ago, during the late Pleistocene, the geodynamo entered one such excursion. The Laschamps Excursion, named after French lava flows where it was first detected, magnetic field strength plummeted to between 6 and 10% of modern values. At the peak reversal, the field may have reached as low as 0 to 2% of normal strength. The poles wandered erratically across the globe, sometimes drifting toward the equator, occasionally crossing into the southern hemisphere. The field fragmented into a weak, chaotic, multipolar configuration, multiple smaller poles scattered across the planet rather than one clear north and south. This unstable state persisted for several hundred years at its most extreme, with the entire process of destabilization, reversal, and recovery spanning roughly 1,500 years. For life on the surface, Earth's primary defense against space radiation was effectively offline. The magnetosphere normally extends about 60,000 kilometers toward the sun, forming a protective bubble blown back by solar wind. When the field strength dropped below 10% during the Laschamps Excursion, this bubble contracted dramatically. Phenomena normally confined to polar regions became global. Solar wind particles, protons and electrons stripped from the sun, could now penetrate deep into Earth's atmosphere anywhere on the planet. Galactic cosmic rays presented an even greater threat. These atomic nuclei carry enormous energies from supernova shockwaves and move at near light speed, shattering atmospheric molecules on impact. A strong magnetic field deflects most of these particles. A weak, chaotic field allows them through. Collisions with nitrogen and oxygen molecules triggered nuclear reactions, creating cascades of secondary particles. One critical product was nitric oxide and nitrogen dioxide, reactive molecules that efficiently destroy ozone. Ozone exists primarily in the stratosphere, 15 to 35 kilometers up, where it absorbs the most dangerous ultraviolet wavelengths, UVB and UVC radiation. The nitrogen oxides produced by cosmic ray bombardment acted as catalysts, breaking ozone molecules apart faster than sunlight could recreate them. The ozone layer thinned significantly across the planet. With less ozone overhead, more ultraviolet radiation reached the surface. UVB damages DNA directly, increasing cancer risk and impairing photosynthesis in plants. UVC, normally absorbed entirely in the stratosphere, is even more lethal to cellular machinery. The ionized atmosphere produced visible effects. Auroras, usually confined to high latitudes, appeared everywhere. The sky over equatorial Africa, Central Australia, and the Amazon glowed nightly with shifting curtains of red, green, and violet light. Ultraviolet radiation is categorized by wavelength. UVA, the longest wavelength and least energetic, penetrates the skin and causes tanning and long-term aging. UVB has enough energy to damage DNA directly. UVC, the shortest wavelength and most energetic, destroys molecular bonds in proteins and nucleic acids, and is normally absorbed completely by the ozone layer before reaching the surface. During the Adams event, with ozone depletion widespread, surface UV levels increased across all three categories. The magnitude of this increase is difficult to quantify precisely from proxy data, though atmospheric models indicate it was significant enough to produce measurable biological stress. Prolonged UVB exposure increases the risk of skin cancers in animals, particularly in species with exposed skin or light pigmentation. It causes cataracts by damaging proteins in the eye's lens. Populations spending extended time in direct sunlight, hunting on open savannas, fishing along coastlines, migrating across treeless tundra, faced chronic cumulative hazard. Plants faced a different problem. Photosynthesis depends on chloroplasts, organelles containing chlorophyll and other pigments that capture light energy. UVB radiation damages the DNA within chloroplasts and disrupts the photosynthetic machinery, reducing growth rates and seed production. In high doses, it can stunt or kill plants outright. Forests with dense canopies offered some protection for understory plants. Grasslands, tundra, and open shrublands received direct exposure. The ecosystems most vulnerable were those in regions with little cloud cover and high solar intensity, tropical and subtropical zones, and high-altitude environments where the atmosphere is thinner. Desert margins, savannas, and Mediterranean scrublands experienced significant stress. Herbivores dependent on these plant communities faced less predictable food availability. Carnivores hunting those herbivores felt the pressure cascade upward. Neanderthals, having evolved in Eurasia over hundreds of thousands of years, had likely developed lighter skin pigmentation, an adaptation to lower UV levels at higher latitudes that improves vitamin D synthesis in low-light conditions. This made them particularly vulnerable to the increased UV radiation during the Adams event. Modern humans, many of whom had only recently migrated out of Africa and retained darker pigmentation, had better natural protection. The radiation problem was not acute poisoning. Chronic exposure over generations meant higher cancer rates, reduced fertility, impaired vision, and, for populations already stressed by other factors, another pressure on survival. The late Pleistocene was already a period of extreme climatic instability. Ice sheets advanced and retreated across northern continents in cycles. Sea levels rose and fell by over 100 meters. The Adams event amplified this volatility through atmospheric feedback. Galactic cosmic rays ionize air molecules, creating charged particles that serve as condensation nuclei around which water vapor forms droplets. Higher cosmic ray flux produces more clouds, particularly low-altitude clouds that reflect incoming solar radiation to space, causing cooling. Simultaneously, ozone depletion cooled the stratosphere. Ozone absorbs ultraviolet light and converts it to heat. Remove the ozone, and the stratosphere becomes colder. These temperature changes altered large-scale circulation patterns, the polar vortex, jet streams, and Hadley cells, manifesting on the ground as shifts in regional climate. The Laurentide ice sheet, covering much of Canada, experienced renewed growth. New Zealand's Southern Alps glaciers expanded significantly. Australia underwent severe aridification, lake levels dropped, wetlands dried, and vegetation shifted toward drought-tolerant species. These transitions happened abruptly. Greenland ice cores show sudden shifts in temperature and atmospheric composition around 42,000 years ago. The cosmic ray-driven cloud formation and ozone-driven circulation changes pushed regional climates into more extreme states. For Ice Age ecosystems, this meant unpredictability. Mammoths, following established migration routes, found seasonal vegetation had failed. Caribou adapted to the tundra, faced sudden forest encroachment or vegetation retreat into isolated refugia. Predators like cave lions experienced boom and bust cycles in prey availability. The Adams event acted as a climate amplifier, adding new variables that increased the frequency and severity of environmental shocks. Between approximately 41,000 and 39,000 years ago, Neanderthals vanished from the archaeological record in Europe. After roughly 300,000 years of successful occupation across Eurasia, they were gone. For decades, explanations focused on competition with anatomically modern humans, Homo sapiens, who had been expanding into Europe from Africa and the Middle East. Modern humans had advantages in tool technologies, diet breadth, and social organization. Neanderthals, the argument went, simply could not compete. Climate change was acknowledged as a contributing factor, usually framed as background stress rather than a direct cause. The timing of the Adams event suggests an additional mechanism. Neanderthal populations were already small and fragmented by 42,000 years ago, confined to isolated pockets of suitable habitat as Ice Age climates shifted. The Adams event introduced multiple new stressors simultaneously: increased UV radiation, habitat disruption from abrupt climate shifts, and likely reductions in prey availability as megafauna populations themselves came under pressure. Neanderthals' lighter skin, advantageous in low UV environments, became a liability during the ozone depletion crisis. Higher rates of skin cancer, cataracts, and UV-induced immune suppression could have reduced reproductive success and increased mortality, particularly among individuals who spent extended periods hunting in open terrain. Resource scarcity from climate chaos compounded these pressures, potentially pushing already small populations below viable thresholds. Genetic diversity collapsed, making recovery impossible. The Australian megafauna extinctions show a similar pattern. Between approximately 45,000 and 40,000 years ago, the continent lost its largest marsupials: Diprotodon, a rhinoceros-sized wombat; Procoptodon, a giant short-faced kangaroo standing over 2 meters tall; and Thylacoleo, the marsupial lion. The timing coincides closely with both the arrival of humans in Australia and the severe aridification linked to the Adams event. For these large herbivores, the drying of the continent was catastrophic. Water sources shrank or disappeared entirely. Plant productivity declined. Migration routes that had been reliable for millennia no longer led to food and water. Large animals, with their higher absolute food and water requirements and slower reproductive rates, are inherently less able to adapt quickly to rapid environmental change. The Adams event provided the environmental forcing that collapsed their ecosystems. Elsewhere in the world, similar patterns appear. Woolly rhinoceroses, cave bears, and giant ground sloths all show population declines or regional extinctions during this period. Human hunting pressure was real and significant. The Adams event provided a plausible mechanism for why extinctions cluster around this particular time window, a stress multiplier taking populations that were already vulnerable and subjecting them to centuries of compounded environmental pressure from which recovery was impossible. Homo sapiens survived. By 42,000 years ago, modern human populations occupied Africa, the Middle East, much of Asia, and Australia. They had crossed open ocean to reach islands, adapted to tropical rainforests and Arctic tundra, and developed diverse subsistence strategies. When the Adams event began, they responded behaviorally. One of the most striking archaeological patterns from this period is the intensification of cave use. Caves had always been utilized as temporary shelters. Around this time, evidence of prolonged, repeated occupation increases dramatically. This makes functional sense. A cave offers protection from ultraviolet radiation. The rock overhead absorbs UV completely. For populations living in regions with high solar exposure and depleted ozone, spending more time in caves during daylight hours was a simple, effective adaptive strategy. Red ochre, a naturally occurring iron oxide pigment ranging in color from yellow to deep red, shows a marked increase in use during this period. Ochre had been part of human material culture for over 100,000 years, used for symbolic purposes like body decoration and rock art. The intensity and ubiquity of ochre use increased around 40,000 years ago. Mixed with animal fat or plant oils, ochre creates a paste that reflects and absorbs UV radiation, providing measurable protection against sunburn and long-term skin damage. Humans appear to have been using it as a physical sunscreen. The same red pigment was also being applied to cave walls. The oldest known figurative cave art dates to this window. The Chauvet Cave in southern France contains spectacular paintings of lions, rhinoceroses, and mammoths, rendered with sophisticated shading and perspective, dated to approximately 37,000 years ago. In Sulawesi, Indonesia, a painting of a warty pig in a limestone cave has been dated to at least 45,500 years ago, placing it squarely within the Adams event timeframe. In El Castillo, Spain, hand stencils created by blowing ochre pigment over a hand pressed against the cave wall date to a similar period. This sudden fluorescence of art is unlikely to be coincidental. Spending more time in caves, sheltering from hostile surface conditions, increased social interaction within enclosed spaces. The intimacy and isolation of cave environments fostered storytelling, ritual, and symbolic expression. Creating art deep within these shelters could have served multiple functions: establishing presence in protected spaces, transmitting knowledge about animals and landscapes, and strengthening community bonds during a time when the external world had become unpredictable and dangerous. The sky was full of auroras that had no place being there. The sun caused burns that it hadn't before. Animals migrated erratically or disappeared. The creation of art, depicting the animals that mattered, the hands of the people who survived, might have been a way of asserting control, preserving knowledge, or building community cohesion under duress. Environmental pressure, in this reading, did not just threaten human populations. It may have inadvertently catalyzed one of humanity's most distinctive cultural capacities. Reconstructing events from 42,000 years ago requires natural archives, preserving chemical evidence across millennia. The breakthrough came from ancient Kauri trees, preserved in New Zealand swamps. Kauri trees, massive conifers native to the region, can live over 2,000 years. Some fell into peat swamps where low oxygen prevented decay, preserving wood for tens of millennia. Scientists recovered logs from trees that lived through the entire Laschamps Excursion. Tree rings provide an exact annual calendar. By counting backward from the outermost ring, researchers assigned precise calendar years to each ring, then measured carbon-14 concentration in each. Carbon-14 is produced when galactic cosmic rays strike nitrogen atoms in the upper atmosphere. Plants absorb atmospheric carbon dioxide during photosynthesis, incorporating carbon-14 into their tissues. The amount in a tree ring reflects the atmospheric concentration that year. When Earth's magnetic field is strong, fewer cosmic rays penetrate the atmosphere, and carbon-14 production stays low. During periods of magnetic weakness, cosmic ray flux increases, and carbon-14 production surges. The Kauri record showed an enormous, sustained carbon-14 spike centered around 41,000 years ago, too large for solar activity alone. It required a collapse of the magnetic field. The Kauri trees provided a year-by-year timing of the magnetic collapse. Matching the carbon-14 spike to beryllium, 10 increases in ice cores, and paleomagnetic data showing weak chaotic fields in volcanic rocks and sediments, scientists synchronized all evidence. The magnetic collapse, cosmic ray bombardment, ozone depletion, climate shifts, and biological changes were all happening simultaneously. The Adams event was real and global. Earth's magnetic field is currently weakening. Over the past 2 centuries, global field strength has declined by approximately 9%. This is not unprecedented. The field has fluctuated throughout human history, though it is measurable and ongoing. There is also a large and growing region of reduced field strength stretching from southern Africa across the South Atlantic to South America, known as the South Atlantic Anomaly. Satellites passing through this region experience higher levels of radiation exposure, leading to occasional malfunctions. The anomaly is expanding and intensifying, which some geophysicists interpret as a possible precursor to another geomagnetic excursion, or even a full reversal. Reversals and excursions are not rare events on geological timescales. The last full reversal occurred approximately 780,000 years ago. Excursions are more frequent. Several have occurred over the past few million years. The Laschamps Excursion itself is simply the most recent well-documented example. Another will occur. The timing remains uncertain. From a natural perspective, another Adams event presents familiar challenges. The ozone layer thins, UV radiation increases, and climate patterns destabilize. Ecosystems adapted to current conditions face rapid shifts. Species already stressed by habitat loss and climate change face additional pressure. The biological impacts resemble those of 42,000 years ago. Increased extinction risk for vulnerable populations, particularly large animals with slow reproduction. Modern civilization now depends on infrastructure extraordinarily sensitive to geomagnetic disturbances and space radiation. Satellites provide GPS navigation, telecommunications, weather forecasting, and Earth observation. A collapse of the magnetosphere exposes these satellites to intense solar and cosmic radiation. GPS and communication networks degrade or fail. Electrical grids are also vulnerable. Geomagnetic storms, disturbances in Earth's magnetic field caused by solar flares, induce electrical currents in long-distance power lines. A powerful storm, amplified by a weakened magnetosphere, could overload transformers and cause widespread, prolonged blackouts. The 1989 Quebec blackout, caused by a relatively modest geomagnetic storm, left 6 million people without power for 9 hours. A storm during a magnetic excursion could be far worse. Aviation faces increased radiation exposure, particularly on polar routes where the magnetic field is naturally weaker. Passengers and crew on high-altitude flights receive higher doses of cosmic radiation, requiring route changes or flight restrictions. Navigation systems dependent on satellites and magnetic compasses become unreliable. The natural world adapts as it did before. Ecosystems shift, some species decline or vanish, and new equilibria emerge over centuries. For human civilization, the challenge is different. Maintaining complex, interconnected technological systems during a multi-century period of geophysical instability. The Adams event offers a preview, not of what will happen, but of what can.